Hi everyone. We are Team Anote 1A, and our project is about fine-tuning financial LLMs. Next slide, please. So I am Sunny Song from Rice University, and we have a teammate called Aisha Melki from Hunter College. She's not here today, unfortunately, due to her personal issue, but she recorded her part and will share with us in another way.
Hi, my name is Rena. I go to Cooper Union. I believe that's, oh, sorry.
That we have a teammate. I'm Oluwamaya Konlaole, and I go to Fisk University. And our teammate Swati is unfortunately not here as well.
And we definitely wanted to mention a special thanks to Jatin and Nathan for supporting us throughout this journey and, helping us out whenever there was difficulty.
Yeah, and so the agenda we're going to go over today is that we're going to start with our project goal and the resources and approaches we used in this project, the dataset we tested on, and the final modeling result.
Sorry, I was muted. So to begin with, we kind of set this goal at the beginning when we first received our challenge, but kind of wanted to reflect on why we kept this goal. So our initial goal was to challenge was to develop an AI model, which we kind of changed into fine-tuning the model instead of actually developing it. To accurately answer financial questions, which were either numerical, categorical, and using the BizBench data set mainly to fine tune it. So we kind of stuck with this goal for the most part, except for the moving from developing to fine tuning, I would say. But yeah, we definitely wanted to include it to kind of show where we've grown from. So the idea, kind of the birth of our project, I would say, happened when we decided we needed a pre-trained LLM. So to identify a model that was pre-trained and suitable for financially focused large language models. And we'll go a little more into which models we looked at and the ones that we used. Sorry. Then we knew we had to fine tune this model based off of different data. Luckily, Nathan gave us this finance benchmarking data, and we were able to use that as a really nice working point. And then finally, we knew we had to optimize the model. So to explore and assess the fine-tuning techniques to optimize the model for financial data specifically, because this model was such a niche targeted model. So where we kind of went from after almost like mapping out the idea, we decided to select the most effective technique and apply it to further refine the model. We went through a bunch of stages of finding new techniques, testing them out on different data, testing them out on different models, as we'll go into a little more later. But eventually we did have to just choose one and stick with it. Then we evaluated the model's performance using testing data in order to make sure it met certain standards. Had a lot of issue with this stage, I will say. Again, we'll go into it a little more later, but this was definitely a hard point. And then we decided which techniques can be combined in order to create a new potential model. This is half what we've done and half what is kind of there in the future to be done with this model. But yeah, just a little map of where we went.
Okay, so for business impact, the first is enhanced efficiency. So by creating a customized chat box for financial companies, we're able to streamline operations with relevant and accurate inputs. It's also secure and private, so these companies don't have to rely on third-party chatbots, and they can solely use models that were created in-house. Highly accurate, meaning that because this model would be fine-tuned specifically to financial questions, it would outperform generic searches. Yeah. And then optimums for finance, reliable answers to complex financial questions. Next slide, please. Okay, so the resources leveraged were Google Colab and Jupyter Notebooks. And how we basically use this was we would think about what we wanted to do specifically. We would create a goal, and then we would each work on a Google Colab, and then afterwards share what we did. And yeah, for model exploration, we used Hugging Face to find all the models we eventually used for fine tuning. And then the different programming libraries we use were Pandas, NumPy, Re, ASD, and the machine learning libraries we use were the Transformers library and the Hugging Face library. And that's what we use to fine tune our model. And then for hardware acceleration, Torch for GPU optimization. And then the AI tools we use were the Auto Tokenizer and the Auto Modal for casual LLMs for customizing and deploying our language model. Next.
All right, so for our approach, we first started with model exploration. So we researched various pre-trained models on Hugging Face, and our goal was to select a well-suited model for its capability to handle financial text. And this was because we want to essentially feed this model financial queries for it to answer. So after this stage, we looked into selecting specific models. So we were experimenting with models with different sizes and various different parameters. Some of the models that we looked into were smaller and lightweight in comparison to models that were larger and more complex. So our goal in this stage was to evaluate how different sizes of models and different model architecture could impact things like performance, memory usage, and processing speed. So after this stage, we started looking into fine-tuning optimization techniques of these models. So this stage includes things like modifying select parameters within a model, and this is to increase its accuracy in predicting answers to our financial queries. So after this, we also wanted to look into supervised fine-tuning, where we give the model domain-specific data set and train it on the data set to improve the model's understanding and accuracy in specialized contexts.
That was our teammate Aisha who was able to record on the side, just, you know.
Okay, so our data was actually provided to us by Nathan, thankfully, and it was the Finance Bench data set, and for testing, it was the Kensho testing data set. And the questions were domains specific to to the financial world. And then the questions were they were split into two. There were short answer questions and then multiple choice questions. So yeah. Next. So, a problem we ran into was that the fact that the model was just too large. And so these are just the base for the Google Colab GPU that we had access to. So these are just the three things that we decided to do. The first was to quantize the model, which Jatin actually told us about. The second was to split the data. So instead of using the full data set to just use a percentage of it. And then if those two steps didn't work, we just went ahead with a new model. And at the end, we eventually created our own testing data file in order to evaluate our model at various steps. So, yeah. And this is just a list of all the models we used. So the first model is a model called Llama 3.1 AB, and it's an 8 billion parameter model from made by Meta. And the pros are it has high parameters, so it increases the potential accuracy and performance. However, because it is 8 billion parameters, that's a lot to try to train on Google Colab, and so we weren't able to use that specific model. So afterwards, we decided to go with the quantized version of the Llama 3.21b. And it's quantized, making it easier to use with smaller compute resources. However, we figured out that if it's quantized, it's really hard for you to actually change those parameters. And so we also weren't able to fine-tune this model. The next model we went with was the LMware Blang model, and it's known for being a very small model and you don't really require a lot of GPU. And because of the small size, we were able to fine tune it and run it on Google Colab. However, because it's so small, it's not going to perform as well as a model that has 8 billion parameters. And then the last model we looked at was the quantize 1.1 billion parameter model by Open Orca. And it's small and quantized, making us able to use it on Google Colab. However, it's less powerful than the larger models mentioned before. So, yeah.
Yeah, thank you, Malcolm. So, as Malcolm just mentioned, we did further experiments on different models and also tried testing the performance of each model with different datasets, taking the stats from the finance bench data from Patronus AI as an example. So we run the Llama 3.21b instruct quantized model and calculated the accuracy, residual, and mean absolute error of the model's prediction. So this one is not doing a very ideal job. It's giving us an accuracy of 6.98% with a residual of 1,094 and an absolute mean error of 2,435. Next slide, please. So for the Llama Bling model we found, this one's giving us a 9.68 accuracy, a little bit higher with a residual of 3,000-ish and absolute mean error of 4,000-ish. Next slide, please. And for the last one, the Tiny Llama 1.1b model we found, this one is giving us a little better result with 13.04 accuracy, 1,008 residual, and 2,600 mean absolute error. So this one's probably, in general, the best one we found with small size of parameters, and we are planning to do more exploration on this one. Next slide, please. So for a summary, we explored different pre-trained models on Hugging Face, including but not limited to Llama, Bird, Gemini, and we decided to go on with Llama for this high performance and smaller model size. But with experiments, we do notice that foundational models are pretty inaccurate in predicting number-related questions, and those are like most type of questions exist in the finance industry. So that is what we need to work on better. And we did study different fine-tuning concepts and methods like the supervised fine-tuning, LoRa fine-tuning, prompt-based fine-tuning, REJ. So we attempted to run each method on the model we selected, and many of them had a good start, but we haven't been able to reach a point of complete fine-tuning and having the fine-tuned model to successfully predict very ideal outputs. That's because we didn't have available access to any GPU or cloud computing power that can support our fine-tuning operations. As we all know that fine-tuning requires large-scale computation that normal computers, CPU, and RAM can support. That's why we spent more time on searching smaller models or more efficient fine-tuning methods that can be supported on our the current computing resources we have. However, even though we haven't reached a very ideal training result, we do recognize the insight that computing power and enough data size volume is very important for a successful research in ML. And I guess that's everyone who's doing more research in ML should focus on getting and be careful with, so we can have a more successful journey in the research in this field.
So kind of to end off our presentation, we wanted to talk about potential next steps for where we can see this project going, or where there's kind of a need for this project to be further developed. So we'd love to test our model against other large language models to find more ways to optimize it and generally make it perform better. Obviously, being students, we have a limited knowledge on how to fine tune and kind of where we can go from there. So learning from other large language models would be very educational. And then adding in data pre-processing in order to clean and normalize data sets. We had a lot of trouble with the data sets, deciding, how are we going to process them because they were quantitative and qualitative. To remove outliers and ensure domain representation, we would definitely need to have some sort of pre-processing process. And then finally, hyperparameter optimization. So we also wanted to have this to be performed in order to experiment with quantization parameters. But since we only realized we had to quantize our model kind of almost halfway to 3/4 way through, not really possible, but this would minimize accuracy loss and use validation sets for tuning. So make the model a lot more efficient and a lot easier to fine tune. And yeah, that's it for our presentation. I hope you guys enjoyed learning about it. I know we definitely enjoyed working on it this semester.
Thank you so much, team. That was really awesome. I really appreciate you guys' hard work. I thought it was a really interesting presentation. Round of applause, everyone. I have a few questions, but before I go, I was wondering if anyone else has any kind of questions or comments. Okay, cool. I'll ask a few then. So I guess I thought the talk was really interesting. I guess to confirm, so on like the training runs you were showing the results for, that was on like the finance bench data set, but not the Kensho benchmarks one, right? Okay. And you mentioned that you were like evaluating with like accuracy, residuals, and one other metric. I was wondering if you could kind of go into some details on like how you did like the evaluation and what that process looked like.
Yeah, for sure. I can talk about it. So, since we wanted some statistics about the accuracy or residual of the model's prediction, you provided us a lot of data sets, but we found this one has the actual answer to each question provided. So we thought this might be a good choice to evaluate the model on. And when we further look into the data set, we noticed that the data set has different kinds of questions. Some are like more text generating questions, some are metric focused questions, which means like these are questions that require numerical answers. So we thought questions with numerical answers might be a better choice, since we can actually calculate like how far the model's prediction is from the actual one. So we did create a predictor class that will first filter all the questions in the data set with only numerical answers, and also do some pre-processing on the data set to eliminate all the dollar sign symbols or percentage sign symbols, so that we are only left with like pure numbers for the answers. And then we take out the questions as model input, feed to the model to predict results, and then finally take the output and then compare to the given answer, and then calculate for the accuracy and residual. So accuracy is calculated when the outputted number is within 50% tolerance from the given answer, and residual is like purely calculated from the absolute, like the how much different it is from the actual number. So that's how we calculate it.
Okay, so if I understand what you're saying, the accuracy measure was only on like numerical answers to questions?
Yeah.
And then the fine tuning you guys did, was that on like the training set of finance bench, or like what data set did you use for like the fine tuning?
Yeah, it was sorry.
you can go.
I was just gonna say it was the training data that you provided to us in the GitHub, I believe. So yeah, that it definitely included quantitative and qualitative data, but I think as Sunny was mentioning, it was kind of tough to evaluate the accuracy, I would say, of the qualitative part of it. So we found more success in kind of focusing on the quantitative part, and I think we also all kind of work more numerically, so it worked a little easier to do that. Not the ideal result, but it definitely helped in terms of like actually outputting an accuracy score.
Yeah, it makes sense because if it's a number, you know if it's like right or wrong, or if you know like what the tolerance is. So I guess to confirm what you were saying is like both the models that were fine-tuned and the models that like weren't fine-tuned for like the numerical answers to questions, it just like struggled to understand the numerical context and really get that like super right, but the fine-tuned models worked like a little bit better than the zero shot. That's correct, right? Yeah.
Yes, yeah.
And I think it's a pretty common disadvantage for all current language models, because language models essentially they're trained to generate more outputs based on the patterns of given inputs. But when we talk about patterns, it's more like words related. It's not really taking in any mathematical logic to do those mathematical calculations. So that's why I think most language models currently are unable to actually do mathematical questions and then self-related questions. So what I think, if we want to like do a better job with having the models predict on financial questions, we can probably incorporate an extension on letting the model to connect to like an actual calculator or something else, that when we read the question, we get the numbers that need to be calculated, we give it a designated formula, then connect to the calculator and let the calculator do the mathematical part. I think that will be much more accurate than letting the language model itself to generate a number, because the model won't generate a number based on mathematical formulas, but rather generate one based on like letter patterns, which won't really lead to an accurate result.
Understood. So it's like you think it'd be cool if there's like a way you could incorporate like the LLM with like a tool that can actually like understand the mathematical operations rather than just doing tokenization. I guess one more question. I guess did you guys like learn a lot from this project? And if so, if you could like list like a few things that you like learned that you like enjoyed working on, that'd be like cool. Yeah.
Yeah, I can definitely start. I learned a lot. I come from a little more of a mathematical side when it comes to data science. I'm not very much on the computer science side. So first of all, I learned kind of how that works, how an LLM can be set up. And honestly, I learned a lot about working with a team and kind of how working towards one goal is both like unifying, but also it kind of makes you have your own opinions on everything, and like coming together and being able to like agree that okay, yeah, maybe this is not the best case, and going to something else. We did a lot of that. I would say kept pretty consistent with our weekly meetings, so it definitely helped that everyone who was there was contributing. But yeah, I definitely learned a lot about how to actually work with an LLM and like what that actually entails on the back end, rather than just like complete software engineering or math.
I can go next. I would say for me, like prior to this project, I didn't really know a lot about LLMs in general. And it was just very interesting to just be like put in this project and just like learn the different fine-tuning techniques, and then like fail a bunch of times, but like try different techniques and just like go through different processes over and over again. So I'll say that this definitely like taught me how to like fail and then like try again, I would say. So that's one thing I really enjoyed about this project, just like trying different methods and learning new things.
And one thing really important to me is before actually going into the project, I generally think like what a model can do is what I usually see when I use ChatGPT. So right now, I think most people would assume that LLM is capable of what ChatGPT can do. But when we actually try some of our own models, we do notice that it's actually pretty different. If we have a foundational model, we do need to do works like processing or like tuning it, prompting it properly in order to let the model give some ideal result. And those are things that we cannot directly see from using the GPT platform. So yeah, so I think with that, we are learning a lot more about how to actually use some technology that's new in the world. And with this experience, I believe that when we meet more like new technologies coming out, we will be able to use the skills we learned to interact with them more technically and be able to train it, fine tune it to let it meet our goals better.